So let's continue where we ended. And another way of using the PCA is the shape tensor. And one thing I didn't say about the PCA is actually what you do is you create a transformation matrix for that rotates the data in a way that you have your maximization in different directions. And that is important, as I said before, looking at cells usually don't have them well aligned with X and Y axis. And with the help of this, we can actually rotate the coordinate system in a way that it best fits the object. And here we have our decomposition. We have the covariance matrix of different positions. We do the eigenvalue decomposition, and then we look at it on this blob, which you can see is slightly rotated just by eye. But now we're going to measure it, and by taking the coordinates we have in this image and do the PCA analysis, do the fitting, we can see that our principal component axes, they are actually oriented in a way that we would say from the gut feeling that it would be rotated. So it actually makes sense. So the math can help us to find these best orientations. And then afterwards we can of course apply the transform, and then it's rotated in the best way that we could get from this one. And well, we can do a lot of transformations. We can do data reduction with the principal component. We can also get orientations. So it's in the right application, it's a very useful tool. If you have a lot of data, you want to look at these orientations. And actually, I'm going to skip this because otherwise we are getting a bit late. So what we have done in this first part is first component labeling, identifying our objects. We have described got different object descriptors, and with the help of PCA, we can reduce the data or look at orientations in the data. And then we have the next part, which is this one. So let's go on and looking at more shapes and something called texture. And again, lots of literature. And also, I think I ran it actually, but let's do it anyway for safety. So now we're going to look in something called distance maps and thickness maps, and also characterizing shapes and looking at textures in the images. And one question is how we can measure the shape of complicated objects. Now, looking at just the area and perimeter doesn't really tell how an object is behaving. We can also look at where we are within the object, and this is what we want to look at now in this part of the lecture. Another thing is patterns, how we can quantify patterns within the image, and also compare different patterns and trying to make conclusions from it. So, for example, the radiologists say something is looking evil. What makes him say that it's evil? What is evil? And that is usually a question about he sees some kind of patterns in the blob that he observes and sees that, okay, this one doesn't behave right. But characterizing this pattern is the question how to do it. So the first thing we are going to look at are distance maps. And in principle, it's a new image that actually maps distances within the image. And each point can be measured. So the distance map either is measured from is always measured from the perimeter of the object, either outward or inwards into the object. And that one would be more information than what we can do with the surface of an object or region of interest or center object or something like that. And again, we have different ways of looking into these metrics, and it's again based on, to some part, the neighborhood, but also directly Euclidean. So we have some different metrics here. We have Euclidean, we have city block, and we have checkerboard. And that's the 4 and 8 connected neighborhoods. So if we look at the city block, that is the analog that you're actually walking around in a city, and you can just follow the streets. And the distance you get when you do that is, of this distance here, is 13. And that's quite far, because you can't take the diagonal. If you do the checkerboard distance and just count the pixels on the way, then you get the distance 8. And if you look at the Euclidean distance between the starting point and the end point, you get 8.6. Now, the critical mind can say that, okay, counting pixels may not be the best. Maybe we should, in the diagonal, count square root of 2 instead. Doing that, you will get to somewhere around 9.4, I think it was, when I did that. So that would mean you would get a little bit overestimating the distance. So these, they are good because they are fast, but you have to take into account that they are not so exact. So what does it look like? First, we need to generate a test image, which is this blob, which is symmetric in this case, so it's an easy one. But anyway, we have a background, which is 0, and we have a foreground, which is 1. And now we want to measure how many pixels from the background into the foreground we have. And doing that with the Euclidean map, we see that the first one, the boundary here, is 1. Then when you have the diagonal, we have 1.4, which is square root of 2. We have 2.0, which is this one, 2.2, 3.2, and so on. So this is what this the Euclidean distance map would give us. So we go in discrete steps, but each pixel has at least as good as the Euclidean distance can tell. In some implementations, you say that the first pixel is just a half pixel, so that would be a half from the edge. But in the typical implementation, it's from 0 to first pixel, it's a 1. Then when we compute this, there are different algorithms to do it. And if we use different, let's see now. Yeah. This is the Euclidean distance transform. This is the brute force distance transform. Oh wait, I think the labeling is strange now, or I'm one step before. Yeah. Anyway, this is the wrong title of the slide, because this actually shows Euclidean distance in using different approaches. So this one gives essentially the same. Those two, it's a brute force, and it's implemented as an exact transform in scikit image. And that one is using a different algorithm called chamfer. That's an approximation to the Euclidean distance. And the important thing to look at here is the execution time, that this one took 11 microseconds, this one took 20 microseconds, and that one took 8.8 microseconds. And why the speed matters is the question. So on the microsecond scale, you don't care. But if you have a large, even 3-dimensional data set, then you start really to care, because then it really takes time. And the extrapolation here, using these different transforms, is we had these execution times for this image was 13.5 milliseconds, this was 400 milliseconds, and this was 2.7 milliseconds. You see, these two have about the same quality, but that one looks a bit weird. And the effect is when you compute it on the large volume, it would take 0.2 hours. This one would take almost 6 hours, and this one would take 0.04 hours. So there is a great gain in using a fast algorithm. And the question is if you want to use how you want to use the data afterwards. This one looks pretty good near the perimeter, but the further in you get, the more wrong it gets. So if you can live with that in your application, then it's fine, because then you can do faster processing. Otherwise, you have to go to this one, which is 5 times slower, but then you have the exact value. So that is what you need to think about. And in particular, if you want to process many of these images, then you really have to decide what quality do I really need. This is a kind of an ugly piece of code. To do it, to compute a simple distance iteration, you need to run 4 different loops, a lot of ifs, and the outer loop is about just scanning the image, and the inner loop is scanning the neighborhood to find the shortest distance within that neighborhood. And afterwards, it repeats and goes all the way in. Looking at that, we again create our test image. Now I think I need to actually execute that one and execute that one. And then we can see how this algorithm propagates step by step. And first, it's just a pre-labeling of 255, and then it sees that first ring gets the ones, and then you get the twos, and so on. So it iterates. It's a kind of same kind of brush fire iteration that you saw in the labeling algorithm. And again, distance transforms can be done in different ways. And as you saw, this particular approach is very slow. So it's more for showing the principle of how the iteration works. So that's why I'm not going to go too deep into this implementation. The other distance maps, then you change the distance metric to have the a different one. And so that would be the city block. And here you can see how that one behaves. You can see that it only has integer values in the distance. And here you have to look at some different things. So what we do is, first of all, we cannot measure anything below the pixel size. So that is the shortest we can do. And it also needs to be, of course, physical meaningful. Typically, we do imaging with cubic voxels, but in, for example, medical imaging, when you do slices, sometimes slices are anisotropic. So instead, they have x, y, they are the same, but the z along the axis of the patient may be a lot thicker, so they create much thicker slices. And that also needs to be included in the distance calculation. So there you need a custom distance map to handle that kind of anisotropy. So what does show? Here we have 2 cases. We create distance map of 2 cases, one from the foreground into the background, and the other one going from the background to the foreground. So we have this bi-level image, and if you go to from, they have flipped. Okay, from that is actually from background to foreground, and that one is the opposite. And you can see here you have a lot of zeros around the object, and you have the distance within the object. And you can, of course, also compute it in the other way around, and then you have all the distances between objects in principle. So that is something we can look at in a case here. We can want to look at how distance map can be used actually to determine the shape or distributions in an object. And if you try two ways, one is to work with we have two growing objects, and if we compute the distance map, you can see that you have about the same distribution all the time. Whereas if you try to component labeling and compute the area, you can see that in the beginning you have two items. They're growing, 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 and then all of a sudden they touch each other, and then the component labeling cannot separate them, and all of a sudden you have a very large object instead, and that is what you see in this curve. So here we can say that the average distance actually is a better metric than component labeling and area measurements. So that's a little bit to see the contrast of what different methods can do for you. Looking at real images, that's actually where we want to go. And now we take this bone slice, and we have the mask with different cells and channels. Looking at the distance map of the foreground, you can see small blobs here. This one is larger, so you have larger distances. These are just small ones, so you more or less just see them in blue. That can tell things about the objects themselves, but if you look at the background distances, then you can tell how separated they are. And that's another difference, another information which may be interesting to you. That you could, in principle, also do by computing the centroids of each one and compute the distances between them, but here you get a distribution of distances in the object. The cortex is more, in this case, more a playing example, that we just have a structure, and you can see here very nicely how the distance transform look like. And if we look at the distances, you can see here the histogram of distances within the object, and you see that there are not so many on the longer distances, and that's of course because we are only here in the middle. This is heavily downsampled, so you can see the distances. Another useful method to use the distance transform is to compute averages as function of the distance. So in principle, you're going to have iso shells with the same distance, and then you want to compute gray levels, porosity, or something like that. And then you find all the pixels at a given distance, and then you compute some kind of average from that. And then it's like peeling off shells of an onion, and you measure each individually. And that is something I did in this little demo. You have it on the GitHub, or you can actually also click on that one. Here we wanted to look at this. This is some kind of sand, soil, and we want to see the water penetration in it. And what I did was I computed a distance map from the soil surface down into the object, and then I computed the average intensity in there. And when I plotted it, I came out with a curve like this. So we can see that there was more attenuation in this part, in the upper part, close to the surface, than in the upper part. So this was the kind of investigation you can do with the help of the distance transform. All the steps I did are in this notebook, so if you want to look into that, there is more information to go for. Cousin to the distance map is a thickness map. It's almost the same, but anyway different. So in this plot here, you can see what the distance map looks like and what the pore size map looks like, or thickness map. They have different names depending on which area you're working in. And what it does is, in principle, it looks at a pixel and sees which is the largest distance within the radius of that pixel. and that is the value that you plot. So when you're outside of an object, here you can draw a ball which is much larger than you can draw when you're in between these two. So what it gives you is the largest ball that you can press in that local position. And that is used, for example, then in a lot in porous media analysis. And here we have some examples. It's a bit small now, but you can see it in the lecture notes. But anyway, this one, here you can see what the distance map looks like. It has a very bright ridge that tells, in principle, the radius at that point to the next wall. But this one tells what is the largest ball that you can bring in, and then you have a larger pore size here. And that can give you pore size distributions that can help you to do water flow simulations afterwards. That can also be implemented. I'm not going into the steps, but more looking now to what it looked like on the bone image. Within the objects, it's not telling you so much maybe, but here you can tell, when you look at in the background, you can tell more about how separated these objects are. And looking at the histogram of these, you can see that the distance map is much more weighted towards the small values, whereas the distance map does that. And the thickness map is better at actually pinpointing how large these objects are. Same here in the background. You can see that the distance map gives you some average distance, but this one gives you a better notion about how large actually the space is between the objects. And of course, we can do the distance map in 3D. And that's just a little bit different neighborhood, and then it works on. Here we have a 3D image. It's quite a large one. It's 100, no, not so large, but larger than we can display easily. So it's 150 cubed about. And here we look at every 10 slices in the image in 2 different directions. And we can see what these blobs look like. And in the axial plane, you can see they are more or less round. And in the vertical plane, they are more elliptic, so it's probably some kind of oblatoids and these shapes. And that can be rendered using a surface mesh. And meshing is an operation that is helpful if you, for example, want to do finite element simulations. Then you use all these little triangles to identify points or nodes in the simulation. And with that, you can propagate your simulation through the object. And another way is actually what we do here is for the rendering. So as soon as you do some kind of 3D rendering of an object, you do, as the first step, you do this kind of triangulation. And then the graphics algorithms, they make nice surfaces and shadings, etc. on the structures. And here is an example how we got one of these surfaces. We can also rotate it, so it's a nice thing. We can set the threshold, I think. No, update. So there we got it, and then we can see different sizes of the blobs. So this is what you need, what you can use the mesh for, and that was just a little intermediate thing. But now we have our objects, we compute the distance maps, and you can see again how it is in 3D. Actually, you see the shapes much better in this way. Then we can also look at the thickness map. This is some kind of foam. I think they did cafe latte foaming and looked at the bubbles in that. So they did actually a time series scan, looking how the foam was building up and how it afterwards collapsed. And here you can see how which different thicknesses we have in the foam. And then we got some indications about how thick the objects are. So this is a so-called max projection, which is the same as if you look at the image from different planes and take the maximum through that plane. And that's a way how you can, in principle, quickly in 2D show distributions of a 3D object. And here we have the different planes. You can see also again they're color coded now for the bubble size. And yeah, then we can also look at that. Yeah, interactive 3D views would be to use the IPy volume tools. I'm not going to show that here now. Let's see. Oops. Let's see. I got a bit lost here now, sorry. Yeah. I think I skipped those two. Instead, we go to the meshing. I mentioned this meshing before. And here you have a very nice example how the meshes look like. The question is how you can get these meshes. Because they are not, you don't know, you only have the voxels in your image. And the way how to do it is to use something called the Martian cubes algorithm. And that one is here, yes. The Martian cubes algorithm is that if you imagine you have a cube with 8 corners, and these corners, they are lying on either on the outside or inside of a surface. And depending on where they are located, you get a specific constellation. And this specific constellation of corners gives you a specific triangle in your rendering. And then you let this cube march around. And sometimes you are within the object and you don't do anything. If you are at the edge, then all of a sudden, say like that one got lost, then you do a certain triangle. If the other one got lost, then you do a different triangle. And this is how this algorithm works. And you don't see it here now, but there is a nice video on YouTube, which is on the slide, but it doesn't show today, that shows it animated, how this algorithm works. And the reason why I want to do it is you have seen this before. When you have small objects, it's not so easy to render them as the real shape they are. And even at this size, if you just would render the voxels themselves, it would turn out pretty edgy. And with the help of the triangulation, you can make a smooth surface, and then you can better render the objects in the 3D renderer. You can also better follow it for your modeling. Curvature is another metric that we can look at, and that can actually be done with the help of filters. But in principle, we want to know how curved a surface is, and that can describe also what they look like locally, and it can also be used for the rendering. And if we have a surface like this, you can define tangenting planes, and with that, you can, in that tangenting plane, you can tell what the curvature is, and also the normal of the object. And then you get a hedgehog like this if you try to visualize those normals. And they also used for the shading purpose. And sometimes you want to also characterize them for some kind of measurement of your object. Right now I can actually not give an example, but the main application I know of is actually to get the right light and shading reflection function of the surface. Then in 3D, we have to define different curvatures in different planes, and we can define them in different ways. You can have the mean curvature, which is just the average value, or you can have the Gaussian curvature, which is the curvature in the two directions multiplied. And these can be used then for different applications when you in particular do the rendering. And here we have some curvature example. It's not so visible actually, a bit not ideal. But we can use them also to measuring and getting structure size from the objects. We can say that the object is going from round spherical faces to more with positive curvature, or we can say we have a lot of saddles with negative curvature. So it can be used in that way. But I say I haven't used these for any characterization yet, actually, personally. So what we can get from the curvature, we can get fold saddle positions, and it's a scale-free metric, actually, to assess how structures are shaped. And well, I think we will leave it with that. Yeah, and then there are also many more ways we can do directional. We can look at tubeness or surfaceness in different applications. But I think we should go on to the texture analysis, because otherwise we will not manage to get that one. So that is an entirely new topic that we haven't touched yet. The world is full of patterns. We have patterns everywhere. If you look at the shades across the street, you can see patterns, or actually the wall or across the street you see patterns. You see patterns on the wall, you see patterns, you see grass fields, etc., etc. So there are quite many different kinds of patterns around in the world. And what we want to do is to try to characterize these patterns in some way. And the name, the technical name we're talking about is textures, and that's the spatial pattern. And to be able to do it, to analyze these, we need to work in regions. We can't just take a single pixel, because it doesn't tell you anything about the pattern locally. And if you do that in regions, you also, of course, suffer in resolution. You can't be that high resolving when you look at these textures. There are quite many approaches on how to analyze textures. So you can have statistical, so then you look at spatial relationships and patterns. Frequency-based, then you try to look at the Fourier transform or wavelets. Gabor filters actually also in the Fourier transform, Fourier domain, typically. Then you can look at periodicity, orientations, or scales. Model-based, then you can do autoregressive models, fractals, to get structural roughness. So then it's more random patterns, like, for example, the wall over there. Also morphological, then you can look at granulometric and getting size distributions in the object. Or you can also look at edge-based, so you try to enhance the edges and look at orientations of these patterns, so it's more for the repetitive structures. Also like the frequency-based, but a little bit different approach. So it's more, it requires really that you have lines that you can work with. We start with some test textures. So we have these ribbed patterns, we have dots. Another one is that we have a smooth version of that one, I think, and that's another smooth version of also some kind of dotty pattern. And then we have the diagonal pattern. And now we want to characterize these in different ways. And one way of doing it is the gray level co-occurrence matrix. And it can tell you information like contrast, correlation, energy, homogeneity, and angular second moment. And looking at those, how we create this matrix is a little beast, because you have many parameters of distances, of gray level variations, and orientations. And in principle, what you do is sum if you have gray level I and gray level j in a certain distance away from the current pixel. So you have here, you have distances and you have differences in gray levels, and that is the information that we look at. And then you do that in many combinations, and in principle it's a four-dimensional presentation for 2D, so it's not so easy to visualize. But let's try. Created a table of different values. We have the position, we have the gray levels. In this case, I'm only going to look at 4 gray levels because I want to reduce the complexity. And we have some distances and we have orientations. So in this example, we're taking these 6 images, or 8. Yeah, anyway. We want to look at 4 levels, 15 distances, and 15 directions. So it's rotating and probing and scanning the image in different orientations. The matrix looks like this, and it's maybe not so easy to follow what's actually happening in here. But we're working in blocks, so we have here, this is 1 block per gray level, and in the black and white we only have 1 block. If we have the 4 levels, then we have the filling the full matrix. Then we have rotations and position differences in this, and then you can see that these give same but relatively same patterns, but they're slightly changed. And the reason why they're changed is that they are 90 degrees shifted. This one is more rippled, so you can also see those dots coming out of here. And then we can look at the average co-occurrence, and then we blend out the gray level differences. And then we get these matrices, and they look pretty much the same, which is a bit confusing actually. But extracting more information from this, we can get some more grouping, some average values. So now we only have distance, theta, and the difference, instead of just having different x and y values. No, gray level values compared to each other, and some energy factor. Applying this to a real image. So this is an image from sea urchin. So this little pointy little thing. And if you cut it up inside, you will see a microscope image looking like this. I did, by hand drawing, I identified some regions which I, with my layman eye, could see in the patterns. And then I overlay that here on the data. So now we try to actually use this gray level co-occurrence matrix to identify information here. And the workflow to do it is we first identify regions from images. First step is also to reduce into tiles. So as I said before, we need to work in different regions, otherwise we don't have sufficient information to look at. Then we compute some feature vectors, so the collocation matrix, and some properties from that. We can look at the histograms, and then we can go on trying to do some kind of clustering to identify these regions. So what the gray level collocation matrix is doing is only to give you the feature vectors. It doesn't tell you really what is what. So the first step is tiling the image, and we do it just numbering it as a sequence number throughout the whole image, and here we see the tiles. And you can clearly see that there is a difference between that tile and that tile, but it's harder to say if there is, so there is no difference between those. Here you get a little bit more confused probably. What is the type of tile we have? Then we compute the collocation properties. We look at contrast, dissimilarity, homogeneity, correlation, and ASM. And the outcome is that we compute this for every tile and store that in a dictionary. That requires some code. So in principle, so going through all the patches and compute the matrix, and then we put that into our dictionary, which is later creating a data frame. And the resulting images from that is first we have the original image. These are the regions that I marked up. Then we have the contrast, dissimilarity, homogeneity, correlation, and ASM. It doesn't really look very convincing right now. We can see in the ASM, okay, there is a darker region down here. There is some kind of band here, but with this coarse resolution, it's still difficult to tell anything. And I wouldn't use any of these images to really make a conclusion. So we can also do some summary of the different statistics. Here we do use the describe function of the data frame, and yeah, it tells us some statistics here. And well, that's just a lot of numbers right now. But let's try some clustering using these information as feature vectors for a k-means. So k-means we did last week. So let's just create a k-means with 5 clusters and try to fit it on the data frame. And the outcome is this. So not very convincing for now. So what we need to do is to see maybe we can combine less information and get a better result. So the first thing we do is to look at the pair plot. Actually, I lost the last row. But here we have the intensity mean, intensity standard deviation, contrast, dissimilarity, and ASM is down here. And we can see that there are some groupings between the standard deviation and the mean. It's more and more overlapping over here. So let's do a very reduced example where we only look at the intensity standard deviation and the intensity mean of these patches. And this I just zoomed up here. Here we see our patches, how I would have labeled them. And then afterwards we can try running the k-means with only the intensity mean and the intensity standard deviation, and this starts looking pretty much convincing compared to what we had before. So this shows how you can do this kind of region segmentation based on local patterns instead of just the intensity. What you can say is that, okay, here I use patches which are 90 by 90 pixels wide. That's pretty large. And to increase the resolution, maybe you should do it in sub-regions or having overlapping regions and let it scan over different regions in a different way. So maybe instead going down to sensitivity regions of 30 by 30, but scanning with overlap of 30 pixels in each direction could give you a better resolution and also better conclusion in the clustering. One comment here is I saw when I had rendered the lecture notes that the segmentation is different in the lecture notes. And the difference is that this blob here only had one color, and instead I had a block over here which was instead clustered, which kind of makes sense because you have larger pores in this region than in the rest. So it is a reasonable cluster. But the reason why I get one here and one there is that k-means starts with an initial guess. It just randomizes all pixels. And depending on which random seed it uses, you get that or that result. In my runs, I actually only noticed 2 different patterns. So it stabilizes into 2 flip-flopping patterns. And how to get rid of it is that you can, in k-means, you can set the initial seed for the random generator of the pattern. So that with that you can get reproducibility in your k-means segmentation. And well, that brings me to the end. So here in the second part, I talked about distance maps, how we can measure distances within objects, and also looking at the pore size, pore radius maps as a complementary information. A bit about 3D visualization and mesh mapping, some about curvatures, and finally a part about texture. And next week I'm going to talk about structure description using skeletons and also advanced item labeling, because we saw that the component labeling actually doesn't really manage to have the touching objects, and that is what we are going to address next week. So, thank you for today.